In this video, we are going to talk about probability and odds. So with probability, we are looking for the probability something would happen. So what's the likelihood that something's going to happen? And there's some rules that go with probability. These probabilities are all numbers between 0 and 1, and we can think about them as decimals or fractions or percentages. So they're numbers between 0 and 1, which means it's going to be between 0% and 100%. We cannot have a probability bigger than 100% because then it's more than guaranteed to happen. And we cannot have a probability less than 0, so we can't have negative probabilities, so it just doesn't make sense. The closer the probability is to 1, the more likely it is to happen. If the probability is equal to 1, then it is guaranteed to happen. If the probability is 0, then it's guaranteed to not happen. When we talk about probabilities, we need to first talk about the idea of a sample set. So a sample set is a list of all the different possibilities for some kind of experiment. So let's say we're rolling a dice 1 time. What would the sample set look like? So I'm going to use S to show sample set. Well, if we roll a die, we could get a 1, we could get a 2, we could get a 3, a 4, a 5, or a 6. So that would be what our sample set looks like for rolling one die. What if we were flipping a coin? Then we're either going to get a heads or we're going to get a tails. What if we were picking an M&M? We would think about all the different colors that are in a bag of M&M. And if I remember correctly, it would be, we could have browns, we could have blues, we could have reds, greens, orange, or yellow. Outcomes of some experiments are equally likely, which means that the chance that any would occur is just as likely as chances for another. So if we're thinking about rolling that dice, then they're all equally likely events. And usually when you list that sample space, you want to list it in such a way so that it's defined simply. And you're listing all the different possibilities where each one is equally likely to happen. Same thing with flipping a coin. You have a 50% chance that you're going to get a head and a 50% chance that you're going to get a tail. And then same thing when you talk about M&Ms. I think that they are about equally likely. We've done some experiments in the past in other classes, and they tend to come out that way. So if we have equally likely events and we want to figure out the probability, then it's the number of elements that are in our probability, what we're looking for, divided by the total. So I think about it as part over whole. Let's look at a few examples. A fair coin, one of which is equal likely to get a heads or tails, will result in a single toss. Is tossed 3 times. What's the probability? 2 heads and 1 tail are tossed. So we want to list all the different ways we could do this. I like to list this by doing a tree diagram. So in that first toss, I could get a heads or I could get a tails. If I got a head the first time, my second toss would either be a heads or a tails. If I would have gotten a tails the first time, my second toss would have either been a heads or a tails. So these are what's called independent events because what happens in the first one does not affect what happens in the second one. And then we would do the same thing with that third toss. So you see how I'm branching off again out of these. So if I had a heads, then a heads, that third toss is going to result in either a heads or a tails. Same thing here. If I would have had a heads and a tails, then I would have gotten, again, a heads or a tails. And same thing down here with these branches. So then we could follow this tree diagram and list all the different possibilities. So we could have had a heads, 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 a heads, heads, tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, or tails, tails, tails. So they're asking us the probability that we're going to have 2 heads and 1 tail. And it does not say it has to be in that order. So we got to think about how many ways could that happen. So let's see, we need 2 heads and a tail. So it happens here. 2 heads and a tail happens here. And 2 heads and a tail happens here. So there's my tablet does not like to draw dots. There's 3 different ways that could happen out of the 8 possibilities. So our probability is going to be 3 out of 8. And we could keep it as a decimal. Or if we wanted to, we could think about it. We could keep it as a fraction. Or if we wanted to, we could write it as a decimal, which would be 0.375. Or if we wanted to turn it into a percent, we could, and they all mean the exact same thing. When we talk about empirical probability, this is theoretical probability. This is what we would expect to happen if it were a perfect world and everything worked out the way it was supposed to. So think about flipping a coin. If we were to flip a coin 10 times, we would expect half of the flips to be heads and half of the flips to be tails. Now, is that going to happen in every single experiment? Probably not. I mean, it's possible that you could get 6 heads one time and 4 tails during that 10 flips. So we've got 2 ways to think about probability. We could think about what would happen theoretically. Okay, that would be that 50% heads, 50% tails. And then we could think about what happens experimentally, what happens in our experiment. Which is also called an empirical probability. And a lot of times what we want to do is we want to compare what happened with our experiment with what should happen theoretically. So how do we compute empirical probabilities? It's still going to be that part divided by the whole. So it's it's the number of times that event E occurred divided by the total number of times that the experiment was performed. So for our last example, that heads and tails, if we had 6 heads out of the 10 flips, then that experimental probability would be 6 out of 10. So let's look at an example. A survey showed the following information on the ages and party affiliations of registered voters in a certain city. If one voter is chosen at random from this survey, what's the probability that the voter is a Republican? So we've got some totals. I'm going to highlight those total columns. If it lets me, my computer is not very happy right now. Okay, so it's not going to let me use the highlighters. I'm just going to kind of separate it right here. So this table is called a contingency table. So they've given us the age brackets, and they've given us how many in this town are registered for those different categories there. And then they've totaled everything up for us, which is really nice. So if I add all those 18 to 28, I would have 847. If I added up all the independents, I would have 499. This represents the total people that are involved in this survey. So we want to find the probability that the voter is a Republican. So it would be part of our whole. How many Republicans do we have? So that's 1038. And that's out of the total, which is 3,228. And that reduces to 173 over 538. As a decimal, it's about 0.3216, or about 32.16%. And this would be about also. So what if I asked, what's the probability that a voter is between ages 29 and 38? I would count how many I have in that category. So that's 804 out of the total. About 24.91%. So you can see how we can read that contingency table. We can also see applications to genetics. You may remember in a biology class somewhere where you looked at parents, different types of things like eye color, hair color, to figure out what are the possibilities they could happen for children. So let's look at an example of those. A child will have cystic fibrosis. The child inherits the recessive gene from both parents. So we have a parent who is capital F, lowercase f, capital F is normal. The lowercase f is going to be the recessive gene. And another parent who is capital F, capital F. And we're going to create that table there. Capital F, lowercase f, capital F, capital F. And so when we create this table, this cell would represent capital F, capital F. This cell would be capital F and lowercase f. This cell would be capital F, capital F. And this cell would be capital F, lowercase f. So we're looking for the probability of getting a recessive gene for both parents, which means two lowercase f's. And notice that we do not have a square that has two lowercase f's, so that means that this probability would be 0%. B is asking the probability that the child's going to be a carrier, which means they're going to have one lowercase f. And in this case, we have two of those, so it would be 2 out of 4, or 50%. And then let's talk about calculating odds. So the odds in favor of an event is the number of favorable outcomes divided by the number of unfavorable outcomes. The odds against an event is the number of unfavorable outcomes over the number of favorable outcomes. So let's look at an example. If a pair of fair dice is rolled once, what's the odds in favor of a sum of 7? So we got to think about how many ways we could get a 7. We are rolling a pair of fair dice, and we're assuming 6-sided dice. So what's the sample set look like? This is a total of 36 possibilities. So what are the possibilities? Well, we could have a 1 on the first die and a 1 on the second die. We could have a 1 on the first and a 2 on the second die, or a 1 then a 3, or a 1 then a 4, or a 1 and a 5, or a 1 and a 6. Or we could have had a 2 on the first one and 1 on the second one, 2 on the first one, 2 on the second one, 2 on the first one, 2 on the second, 2 on the first, 3 on the second. I'm getting tongue-tied today. And you see all those different possibilities. So I'm going to list those out. So there's my 36 possibilities. We want the odds in favor of rolling a 7. So the odds in favor The number of favorable outcomes. So the number of ways we could get 7 out of the number of ways that we have unfavorable outcomes, which would be the number of ways to not get 7. So how many ways can we get a 7 here? We could have 1 and a 6, 2 and a 5, a 3 and a 4, a 4 and a 3. These are different because the order is different. This is a 3 on the first die and a 4 on the second. This is a 4 on the first and a 3 on the second. Same thing with this. That's different than that, and that's different than that. So there's 6 ways that that could happen. There's 30 ways that we could not get a 7, and that would be all the ones that's not circled there. And then that reduces to 1 out of 5. Now, with odds, we usually see those written as fractions or in words or with the colon. So we would say the odds in favor of rolling a 7 is going to be 1 to 5. Odds are going to express a likelihood of an event, and it's related to probability. When odds of an event are known, the probability of the event can be determined. And we could figure that out here using the formula that they're talking about here. Suppose E is an event in the sample space and that the odds in favor of E are A to B. So the probability would be A over A plus B. So our probability was 6 over 30. So the odds in favor of a 7 is 6 out of 30. So the probability of rolling a 7 would be 6 out of 6 plus 30, which would be 6 out of 36, and that reduces to 1 over 6. And you can see that from the sample space. This is a way that we could list that sample space for rolling a pair of die where every option is equally likely to happen. There's 6 ways I could get a 7 out of the 36 possibilities. So you can see that relationship between those. Now, suppose E is an event in the sample space, then the odds in favor of E are the probability of E over 1 minus the probability of E. So we could figure that out here too. What if I know that probability? Then I could figure out the odds by computing this. So if I know my probability is 1 out of 36, 1 out of 6, let me do that down here beside the formula. So it's 1 out of 6 over 1 minus 1 out of 6. So this is 1 out of 6 divided by, this would be 6 out of 6 minus 1 out of 6, which is 5 out of 6. And we do keep, change, flip, which would be 1 out of 5, which is what we got using our odds formula here. So you can see the relationship between odds and the probability associated with those odds. Let's look at one more example. In 2022, the racehorse Rick Strike won the Kentucky Derby. The odds against Rick Strike winning were 80 to 1. What's the probability of Rick Strike winning the race? So the probability of being against Rick Strike winning, or let's talk about the odd rather, odds against was 80 to 1. So then the odds in favor of is that reciprocal 1 to 80. And that's what we talked about up here. You just flip that fraction. That's a relationship between in favor and against. So now we want to figure out probability. So the probability of this event happening is A over A plus B. Okay, that's what they're talking about here. So it's going to be 1 over 1 plus 80, which is 1 over 81. So that would be the probability of Rick Strike winning this particular race.